Hello, my name is Mark. I am a PhD student at SRI Lab at ETH. And today I will talk about several aspects of machine learning robustness in the context of reliable machine learning. So by robustness, why reliable? So as most of you know, the deep learning became a very big topic in 2012, 2013. But in 2013, 2014, there was also this discovery of adversarial examples. So in particular, if you feed this stop sign into a neural network, it will correctly predict the stop sign if it's well trained. But now if you add some particularly well-crafted noise to that stop sign, then as a human, you won't see difference, but the neural network will interpret it very differently. In this case, it will predict the turn left sign. Now, obviously, this poses a large danger. Think of self-driving car making this mistake. So it's important to study these perturbations and how we can be robust to them. And today I wanted to look at three aspects how the study of these perturbations can make machine learning more reliable. Well, first, safety and robustness is like the obvious choice. We want to be robust to these perturbations and we want to show this. Yes, that's quite obvious. Then the other two a bit less obvious. So interpretability and explainability. It's surprisingly connected to this reliability, to this perturbation, to this robustness, to these perturbations. And lastly, I want to look at fairness and privacy, because several of the methods that were developed for the verification of the robustness to these perturbations can be used in other contexts, such as fairness. In particular, I want to showcase today two works that I've recently worked on in my group, and that will be presented at the NeurIPS conference next week. So this is very recent work. And other than that, I generally want to highlight work from my group and work in the field. So let's get started with this first topic on safety and robustness. So great, we have these perturbations that I've shown you. What can we do about them? Well, the obvious thing is to include them in the training process of the neural network. Generally today, I won't go into technical details, but I'm happy to answer them afterwards. Okay, so we somehow include them in the training process. This produces a neural network that is empirically robust to them. So in most cases, it will work fine on these perturbations with some caveats, but will work. But now, can we trust these networks? Well, if we really want to trust them, we somehow want to verify that at least for some given input, such perturbations don't exist. And to this end, there was work from colleagues in my group, so I was not involved in this yet, in 2018, using abstract interpretation to verify exactly this. So normally when you have a neural network, you have this input, let's say this 8 here, and you propagate it through layers. So you have some layer here and some other layer here, and then you have some output, let's say 8 or 9. So this was classified as a digit 8 or as a digit 9. Now, what this abstract interpretation business from my colleagues allows you to do is to take this whole set containing many different perturbations to this 8. So adding noise, as I've shown you, or rotating it slightly, or whatever. So you can take a large set of different perturbations and propagate them through the neural network. Then at each layer, you get a set of all possible values containing the activations for all of these inputs. Then at the end, you can assert that they all classify the same. Then you have proven robustness for this. And based on this work, we in our group have looked at many spin-offs of this work. So improving the certification of this or training on these shapes. But I don't want to go into too much detail on these methods today. I'm sure Patrick will provide some context for similar methods to these. So what I want to talk about today is, so first, one of the upcoming papers that is certified defense to image transformations via randomized smoothing. This is joint work with Max and Martin. So Martin is the prof at SRI Lab. But okay, what does this title mean? So let's take a closer look. So image transformations. Well, in the beginning, I've shown you an example for additive noise, but some research by Engstrom et al. Found it's not just additive noise. There's also geometric perturbations that can result in these adversarial examples. So rotating the image by a very specific angle also can make it, can produce an adversarial example. And then your neural network is not robust on that. So in this work, we want to show how to verify robustness to such perturbations. I will use the example of rotations throughout this presentation, but this also extends to other perturbations. Okay, so how does this certification with this randomized smoothing approach work? Well, let's talk about this additive noise perturbation a bit more before we come to that. So here the attacker adds some noise that we name delta here, and therefore produces this adversarial example. Now, some interesting work by Cohen et al. In 2019 found, well, you can take this image here that already has this noise incorporated, take a lot of copies of it, you take n copies of it, and to each of these copies, you add some deliberately crafted noise. And then you classify all of them using your neural network, and then you perform a majority vote. And then you classify this as the right label, hopefully. And depending on the outcome of the majority vote and how you choose the noise in the beginning and whatever, you can then obtain a bound on the error on this noise that the attacker can add. So if your attacker chooses some noise that's bounded by this here, then you know that you will be safe. Now here's the mathematical formulation. Again, I won't go into details. Now the question is, can we extend this from additive noise to rotations or to general perturbations? Well, yes, that's what we do in our paper, and it works the same way. So we take the potentially rotated image, and we take n copies, and we rotate each of them once more. Then we feed all of them through the neural network, perform the majority vote, and do some math to obtain robustness radius. So in this case, the radius indicates for which angles of rotations we will be safe, and the neural network will be certifiably robust. Mathematically, again, I don't go into details, but generally works. This does not just work for rotations, but it works for some perturbation psi here with an argument beta. So in case of rotation, this argument would be the rotation angle. So we rotate by beta degrees. Mathematically, what is required of this perturbation is that it decomposes like this. So this left side here means if we first apply this psi beta and then apply the psi alpha to our image or our input in general, then this must be the same as performing this combined transformation. So this would mean if we rotate first by beta degrees and then by alpha degrees, this has to be the same as rotating by beta plus alpha degrees. On a high level, we see that rotation fulfills this property. So if we apply this, are we done? Well, no. This makes us empirically a bit more robust, but in general, we can still find counterexamples within this radius. So clearly we have not certified anything yet if we can find some counterexamples. Well, what's the reason for that? Well, image rotations actually don't fulfill this property, even though at a high level it seems conceptually right for this property to hold, but it doesn't. So what's happening? So if we rotate this image by 10 degrees, we get this. And if we rotate it by 20 degrees and then minus 10 degrees, we should get the same image, but really we get a different image. Here you can see the difference. So why is that the case? Well, that has to do with how we save images on a computer. In particular, we save images on a grid of pixels. Now, if you rotate an image, it might not line up very well with the pixel grid again. So computer uses something called interpolation. So it redistributes the pixels on the pixel grid. And you can actually see these threes become different. At a high level, they're still the same three, but that's different enough so that the theorem doesn't work anymore. So what can we do about this? Well, assume we cheat. I give you a classifier HE that treats both of these images the same. So the one that was rotated once and the one that was rotated twice. So if we have this classifier HE, then we can again perform the sampling approach that I talked about in the beginning. And now it works. Well, how do we get this HE? Well, you can do some math and say, okay, I treat the difference between the two images. So here's the image rotated once and the image rotated twice. I treat this as some error and I bound this error by this term E. Now, if I give you this value of E, we can just say, oh, this difference is the same as the additive noise that an attacker can add. So what we can do now to get this classifier HE, we apply randomized smoothing for an additive noise attacker, as we discussed in the beginning. So what we end up doing is we take the image, then we take n copies. For each copy, we sample a different rotation angle. Then for each of the copies, we take again a set of copies, add noise to them, and then we take the majority vote over all of that. And then you get a rotation, then you get a provably robust classifier that, you get a classifier that is provably robust to rotations. Depending on how you get E, this guarantee is a bit different. In the paper, obtaining this value of E is actually quite tricky. We provide 2 ways of doing that. I'm happy to talk about that offline though. Okay, so other topic that I briefly want to cover is interpretability and explainability. Well, here in particular, I want to look at work from researchers from MIT. So if you have a classifier that looks at some input, it is interesting to know why it classifies an input in a certain way. So why is this considered a 6? Why is this considered a bird? Why is this considered a primate? So you want to know which part of the input influences the output of the neural network in what way. So you want to know which pixels in the image influence the output how. Mathematically, this is actually a good surrogate of mathematically for this question is the gradient of the output with respect to the input pixels. Now, if you visualize that for a neural network that was normally trained, you get random, well, not random, but you get a very noisy output that offers you no clear insight. But if you apply the same to a neural network that was trained to be robust to these perturbations, or that employs randomized smoothing, as I've just shown you, then you see that these gradients actually line up very well with what's in the image. So it's somehow clear that the neural network looks at the 7 to decide this is a 7, rather than at random pixels in the image. So this was only a very brief teaser, but we in our group also want to move more into this direction eventually. But now, before my time runs out, I want to cover this last area of reliable machine learning that I want to talk about today. That's fairness and privacy. So again, there's a paper that is that we will introduce in the NeurIPS conference next week. This is learning certified individually fair representations, and this is joint work with Anjan, Mislav, and Martin. So this title is quite a mouthful, but what does it mean? So let's break it down word by word again. So what's individually fairness? Well, at a high level, individual fairness just states similar individuals should be treated similarly. That's a very broad statement. So what does that mean? Well, treated similar is easy in this case. We just say we want them to be classified the same by some machine learning model that does some classification. So think of credit assignment or credit worthiness. So we have a model that tests whether people get a credit or not, and we want similar people to be treated similar by that model. So classified the same. Now, what do similar individuals mean? Well, we'll come to that in a moment. First, let's talk about the other part of the name. What's fair representation learning? Well, here we follow this framework from McNamara introduced in 2012, and that has 3 parties. Imagine the data regulator as some government institution that defines some notion of fairness for a task. So again, if you have credit assignment, they define, okay, we want some notion of fairness, so similar people should be treated similarly. And then you have 2 companies or 2 entities, the data producer and the data consumer. The data consumer is the one that in the end wants to apply the model. So that's the bank that wants to use this creditworthiness test, for example. And the data producer is some other company or entity or government that has the data about the person. So they have some database about people and the features that are important to the data consumer. But also there are features that would allow discrimination against these people. Now the question is, how can we give the data consumer access to just the features? Well, how can we give the data consumer access in a way that he can't discriminate? For that, the data producer produces some latent representation of this data. We'll come to that again. Okay, so given this data regulator, how does it describe similar individuals? Well, in our paper, we say that two individuals, x and x prime, are similar if some logical formula over them holds. This is given by the data regulator. So here is an example. For those that are familiar with this notation, this just means for all categorical attributes of these people, they need to be equivalent, and for all numerical attributes, they need to be close. So if you look at a concrete example, we have three individuals here, and they have a job, a gender, and an income. Job and gender are categorical attributes, and the income is a numerical one. And here we say the categorical attributes need to be the same. So so individuals 1 and 2 are both engineers, and we exclude the gender from this. So they are still similar, individual 1 and 2. And the numerical values, well, it's similar. So for a sufficient value of alpha, individuals 1 and 2 are considered similar, while individual 3 is not. So in this case, if we prove that individuals 1 and 2 are treated the same, then this allows us to show that this model does not bias against gender. So, yeah. Okay, so how does this work? So we propose a model where the data producer and the data consumer both train some neural network or some classifier here. And we leverage techniques from robustness verification to enforce this fairness property. So in particular, the data producer trains a model that takes these inputs, so these representations here, some vector showing these values. So X here is like individual 1, then this brown space is the space of all similar individuals. So individual 2 would be somewhere in this brown space. And then they perform some computation. So they run the neural network on these inputs, perform some computation, and then we end up with this brown area here that is all the outputs for these similar. So for all the similar people, they end up in this region. So to propagate this brown region through the neural network, we use techniques from robustness verification. And then we just take the bounding box here. So we take the center point set and this bounding box here. So that's what the data producer does. Also, to train the data producer in a way that the similar points get mapped to similar, so close together in this latent space here, use techniques from training with logical constraints. That's also something I worked at SRI Lab for my master thesis, actually. Okay, so we take the similar individuals, put them through, and we get this orange bounding box here. So this is given by 7E. Now, what does the data consumer do? So the data consumer, again, takes this box, and they just verify that everything in this box gets classified the same. So same as we had in the beginning with this robustness verification of the numbers. And for this, again, we use techniques developed in the context of robustness verification. Actually, as we will hear from Patrick, this is based on symbolic propagation. If we obtain both proofs from the data producer and from the data consumer, we've actually proven that all similar people, so this brown area here, gets treated the same by the data consumer. And we have thus achieved our fair representation. So this is our fair representation, and we've proven overall fairness of this decision-making process. Okay, so with that, I'm at the end of my presentation, and I quickly want to summarize what I've told you. So we've looked at adversarial robustness in different areas of reliable machine learning. So most obviously, we looked at safety and robustness. So if we know we have a model that has some blind spots, so for example, by slightly turning or perturbing the stop sign, it gets read as a very different street sign that clearly is a safety risk. So we have put lots of effort into training neural networks that are robust to that and to formally verify, so provably verify that they treat these inputs correctly. These networks also are more interpretable for some notions of interpretability, but clearly they look at parts of the input that are more natural to us humans. So when classifying numbers, the actual number. And lastly, I've told you about the applications of these techniques in the areas of fairness and privacy. So in particular, I've shown you how we can use these techniques to verify that similar individuals get treated the same. Well, that I'm at the end of my presentation, and thank you for your attention.
Yeah, thank you very much for your presentation. It was really interesting. Then we will jump straight over to Marc's presentation, and then afterwards we have the Q&A with everybody together. And as Colin is already doing, like, thank you very much for your presentation.
You're welcome. Okay, I'm excited for Patrick's presentation.
Thank you, Marc. Very interesting presentation. Let's see. Can you all see my slides?
Yes.
Yep. Okay, so I'm Patrick, and I'm going to present some work I'm doing with my supervisor, Alessio Lumasio, on formal verification of neural networks via symbolic interval propagation. So we are going to go into a bit more detail on exactly how you can perform the verification. I'll start with quite a lot of background, but I was hoping that Marc would cover the adversarial examples and stuff like that, like he did, so we won't do that twice. So I'll go straight to the verification problem. And as we all know, a neural network is basically a mathematical mapping from an input space to an output space. And as illustrated here in standard operations, we map one input point to one output point. However, in the verification problems, we often try to reason over whole sets of inputs at once. So we may want to ask a question like this. For all inputs in the blue rectangle on the left-hand side there, will they be mapped into some part of the output space we consider as safe, illustrated with the green area on the right-hand side? Now, if we could calculate the exact reachable output area, illustrated with the blue figure on the right-hand side, then this would be a relatively easy problem. But the problem here is, of course, how do we calculate the reachable output area? And directly reasoning over sets of inputs in neural networks like this is difficult due to the high degree of nonlinearity they exhibit. So formal verification methods often overcome this challenge by using some linear relaxation instead. And the idea is that if we have a linearly relaxed network, so we have basically a linear mathematical function that behaves similarly to the underlying network, and this relaxation overestimates the true output of the network, then we can do like this, like you see illustrated on the right-hand side, where the blue figure still illustrates the output of the true underlying neural network. The yellow figure illustrates the overestimating output, and the green is still the safe area of the network. Now, if the yellow area that overestimates the true output of the neural network is within the safe space, then we know that the output of the true network is also within the safe space, and we basically solved our verification problem. So the question becomes, how can we produce such a linear relaxation? And in this presentation, I'll tell you about symbolic interval propagation, which is one of several methods to do this. And symbolic interval propagation calculates bounds for each of the nodes in the networks by propagating linear lower and upper bounds throughout the network from the input layer to the output layer. And I'll show you a quick example here of how this works. We start with some concrete bounds assumed to be given in the verification problem for each input node, and then we initialize the symbolic bounds to the input nodes themselves. Now, these can be propagated through weight layers straightforward because weight layers are affine, so we simply multiply them by the weights and add them together, and we get bounds at the input to the hidden layer. The problem, however, comes now because how can we propagate these bounds through ReLU node with while still keeping them linear? And the solution is again a linear relaxation. So for each ReLU node, we calculate linear lower and upper bounding lines. This is illustrated here, assuming that the ReLU node's input domain is between -1 and 1. This can be calculated from the input equations. We simply calculate this blue upper bounding line and the orange lower bounding line, and we propagate the upper and lower equation through these lines instead of through the ReLU. As a result, at the output, we then get linear equations that overestimate the true output of the ReLU. Doing this, we get equations on the output of the ReLU layer, and we can continue this process then by propagating it through weight layers and through relaxations until we reach the output of the network. There is one thing you may have noticed, and that's if the relaxations of the ReLUs are parallel, the lower and upper bound only differ by a constant factor. There is a version of symbolic interval propagation that takes advantage of this, which we refer to as error-based symbolic interval propagation, or ESIP. And in ESIP, we would propagate only one equation throughout the network, and this equation is always propagated through the lower relaxation of the ReLUs. However, we still have to keep track of the upper relaxation. And we do this by simply introducing a new auxiliary variable, marked as epsilon here. And epsilon will always be the upper relaxation minus the lower relaxation, so 0.5 in this case. Now, by doing this, we get one epsilon value for each node in the network. So here, epsilon 11 is corresponding to node H11, and epsilon 12 to node H12. And having this one equation and the epsilon values at the output node, we can calculate concrete upper and lower bounds by maximizing the equation and adding positive errors for upper bounds and minimizing the equation and adding negative errors for lower bounds. This has some computational advantages, but also ESIP usually produces more succinct bounds than the standard version of SIP, especially for deep networks, because the epsilons can actually cancel out as you propagate them through the network together with the equations. Another interesting thing about ESIP is that the epsilons have a very nice interpretation. So the interpretation is that epsilon ij indicates how much the output equation or the equation at the output changes if we had used the upper relaxation instead of the lower relaxation at ReLU node Hij. Just keep this in mind for later, because later we will use these epsilons as a heuristic to determine which ReLU node influences the network's output the most. Before we go to that, we'll just quickly mention how this can actually be used to solve our original verification problem. And remember, the problem is, will all inputs in the input space be mapped within a safe area in the output space? And we will show how to do this with an example. Assume we have a network with two inputs, x1 and x2, as we had in all examples previously, and one output y. And assume that we want to figure out whether the output of the network is smaller than 0 for all x1, x2 within the input interval. We start the process by step 1 by relaxing the problem, and the relaxation is basically obtained by using ESIP to calculate linear lower and upper bounds for the output of the network. Since these bounds are linear, we can take the upper bound and maximize it. And if the maximum of the upper bound is smaller than 0, then clearly also the output of the underlying neural network is smaller than 0. And if this is the case, we have proven that the property holds, and we say it is safe. Now, if this fails, we proceed to step 2. And in step 2, we try to prove that the property does not hold, that it's unsafe. The way we do this is we try to find an X mark such that the output of the network becomes larger than 0. And we know that such an X mark exists for the upper bound. So we simply use that X mark and run it through the underlying neural network and see if the underlying neural network also produces an output larger than 0. If that's the case, the property does not hold, and we say it's unsafe. And we call this X mark a counterexample. Now, of course, since the upper bound is overestimating the true output of the neural network, this may also fail, in which case we can proceed to step 3. In step 3, we refine the problem, because it couldn't be proven to be either safe or unsafe due to the overestimation in the relaxation. So what we want to do is reduce the overestimation, and we can do this via a branch and bound approach. A simple way of doing this is simply choosing a ReLU node and bounding it to be larger than 0 in one branch and smaller than 0 in another branch, and restart the process from step 1. Now, since these constraints are exhaustive, the ReLU node obviously has to be larger than 0 or smaller than 0. We can say that we know that the property is safe if it's safe in both subsequent branches, and it's unsafe if it's unsafe in at least one of them. So in summary, the foundation of the verification algorithm is we start by relaxing the network with ESIP. We try to prove that the network is safe with this relaxation. If that fails, we go to the search phase. And in the search phase, we try to find a counterexample. And if that fails, we refine the problem and start again from step 1. So this was a very basic approach to verifying neural networks. And now I'll talk a little bit about some contributions we've made, and especially the VeriNet algorithm, which we published at ECAI 2020. Now, the VeriNet algorithm uses the foundation, as we explained here, and it's an ESIP-based complete verification algorithm. It takes us input sets described via box constraints, and that means that each input variable is constrained by a lower and upper concrete value. It is able to verify local robustness properties for classification networks. So basically the local robustness problem is, will the classification of the network stay the same for all inputs within the input set? Our contributions to the algorithm, as we saw before, is first that we produce optimal relaxation for sigmoidal activation functions. We have only seen ReLUs so far, but the algorithm actually works for all activation functions as long as we have a linear relaxation. We introduce a local gradient-based search in the search phase, and we introduce a new adaptive node splitting strategy in the refinement phase. I'll start and talk a little bit about local gradient-based search. And the idea here is that inputs may be mapped to different places in the relaxed network and the real neural network. So an input may be mapped to something that seems like a counterexample in a relaxed network, but it may not be a counterexample in the real network. However, since the relaxed network and the real network are supposed to behave similarly, we may expect that there is a real counterexample in the vicinity of this spurious counterexample. So in an attempt to find some real counterexamples from such spurious counterexamples, we introduce a gradient descent-based local search. This local search is initialized at the spurious counterexample, and then we minimize the loss function, the output of the correct class or the labeled class, minus some other target class we want to be larger. Now, by minimizing this loss function, obviously we hope that the output of the target class becomes larger than the output of the correct class, and we found our counterexample. There is, however, one more thing to remember here, and that's the gradient descent may take xi out of its input bounds. So to make sure that this doesn't happen, we clip xi back to its input bounds after each iteration of the gradient descent. And the idea of this is that we do a quick, short local search around the spurious counterexamples and try to force the input over the decision boundary. So that's the search part. Our next contribution was in the refinement phase, in the adaptive splitting. It's quite technical, so I won't use too much time on it now. But basically what we do here is we utilize bounds from the symbolic interrupt propagation to constrain the nodes in the subsequent branches. We also use intermediate results from the symbolic interrupt propagation in a heuristic to determine exactly which node we want to split. I'll talk a little bit about heuristic. And here is the important part where the interpretation of the epsilons come in. So remember that epsilons are added to upper bounds if positive and lower bounds otherwise. And also remember that epsilon ij indicates how much the output equation would change if we had used the upper relaxation at node ij. So in some sense, it indicates how much node ij influences the output. So to determine which node to split, we simply define a heuristic score function by adding the magnitude of the errors that affect the bounds relevant for the verification problem. After calculating the score for each value node, we simply split the node with the highest score. And our final major contribution here was the relaxations for the sigmoid and tanh activation functions. I also won't go very much into detail on this. But the idea was that we wanted relaxations as tight as possible. And to achieve this, we identified 3 possible relaxations depending on the input domain for the specific node. So I'll just skip ahead there so we can talk a little bit about experiments instead. Yeah, so in summary, we had the optimal relaxations for sigmoids, the local gradient-based search, and the adaptive node splitting. We compared our algorithm against the NeurIPS, which was state of the art, at least at the time. This was about close to a year ago now. And in this plot, we plotted a lot of results for different input sets for 3 different MNIST fully connected networks. We plotted the time VeriNet, our algorithm used to solve the problem, versus NeurIPS. The blue dots are cases that were verified as safe, and as you see here, most of those cases had around a 10 times speed up, and this is mostly due to the adaptive splitting strategy we implemented. More interestingly are the unsafe cases. For the unsafe cases, VeriNet managed to solve all of the cases in less than 1 second, except one, which was like 1.2 seconds. And NeurIPS timed out after 3,600 seconds for several of them. Almost all of this huge gain in performance was due to the local gradient-based search. We also had some other experiments. We showed that we outperformed NeurIPS also on an MNIST convolutional network with approximately 5,000 ReLU nodes. We outperformed the ARAN toolkit on sigma and tanh networks. We did not use NeurIPS because NeurIPS does not support sigma and tanh. And we were able to verify properties of a much larger CFR10 network with about 7 convolutional layers and 50,000 ReLU nodes. That's all I had. Thank you.
Yeah, thank you very much to you as well. So I think we have quite some interesting topics to talk about now in the Q&A. And of course, one big round of applause from everybody around here.